We have already seen one part of the proof, that the first statement implies the second statement. We are heading to prove equivalence of all these three statements, or in other words, we are going to prove that 1 implies 2 and 2 implies 3 and 3 implies 1. Okay. And this is why is this theorem important? So, let us again recall why are we doing this. Here it is, the first property is saying that the conditional expectation, this term, okay, has some continuity property at the boundary. And what is this conditional expectation? Why is it important? Because this is the candidate solution for the Dirichlet problem. We have seen that this conditional expectation as a function of x is harmonic, and also it satisfies the boundary data. Okay. However, it is just a candidate solution because it is not assured that whether this solution can be continuously extended to the boundary. Okay. So, the main remaining missing puzzle piece is that showing that this is indeed continuous, but that might not be true all the time, because we have seen that examples of Lebesgue-Thorne etc., where when the point is not a regular point, we cannot assure this. So, here this first this first statement of this continuity implies second statement. So, that means that regularity of a point on the boundary is a necessary condition. But when we would be able to prove this equivalence, then this becomes a necessary and sufficient condition. Okay. So, if a point on the boundary is regular, then that function can be extended continuously to the boundary, and if all the points on the boundary are regular, then you can do that. Then actually this conditional expectation would give you the solution of the Dirichlet problem. So, that is a background. Okay. So, this is really most important part of this topic, because that would allow us to write down the solution of the Dirichlet problem in terms of conditional expectation of a function of Brownian motion, correct? And then that would give us another computational way to find out the solution. One can actually simulate Brownian motion and find out this conditional expectation. Right? So, this would also give one computational technique also. Okay. So, we have already seen these parts, that 1 implies 2 we have seen. Now, we would see that 2 implies 3. So, let us read 2 and 3 again. 2 is just that point is regular. Okay. A point A on the boundary is regular, and third is saying that if you fix epsilon positive and ask that what is the, ask the probability that exiting time is more than epsilon, okay, given that you are starting from point x and x is as close as possible to the boundary, then of course that exit time would become shorter and shorter, but you have kept epsilon fixed. So, this probability would go to 0. Okay, the most intuitive things, but that intuition works only if A is regular. So, we are going to see that if A is regular, then that implies this. Okay. We first consider function g of x, which is conditional probability that sigma d is not tau d, sigma d is greater than epsilon given w0 is equal to x. So, starting from x, that sigma d is more than epsilon. What is the probability? That we are going to call as g of x. We would like to prove that g of x is an upper semi-continuous function. Okay. Why? Because that property would be required to prove that 2 implies 3. Okay. So, to prove that g is upper semi-continuous function, what we are going to do is that we are going to write down g as limit of decreasing sequence of continuous function. We know that decreasing sequence of continuous function, if that converges to the limit would be at least upper semi-continuous. So, we do that here. So, define g delta x for any delta which is between 0 to epsilon. So, a small number, okay, even smaller than epsilon, g delta of x, that we write down as conditional probability that the Brownian motion stays inside the domain for the whole duration between delta to epsilon. Okay. and given W0 is equal to x. Okay, so this is basically asking that the Brownian motion stays inside the domain for the entire period, which is like here, say for example sigma d is greater than epsilon. That is saying that okay, exit time is more than epsilon. Okay, positive is more than epsilon. And here this is also similar kind of but it is a different event, that say it is inside the domain at least between delta to epsilon. Okay, and W0 is equal to x. Okay, so here this thing I can do using the tau property. I can take condition with respect to a finite sigma algebra f delta, okay, time delta. So when I do that, so this is conditional probability and then expectation of this random variable, because this is now f delta measurable random variable. So Ws is in D for all s in delta to epsilon given f delta, and then this conditional expectation of this random variable given W0 is equal to x. So that we know that these two are equal using the tau property of conditional expectation. Now we try to understand what does it mean. So if I say that first we observe that since W is Markov process, so given f delta, so that conditional probability would be same as if I replace this by W delta. So just the knowledge of the Brownian motion would be sufficient, okay, W delta. And then we observe that this event is determined by the path between delta to epsilon, and W delta is given. So W delta is given and delta to epsilon. So basically we need to look at the path for this epsilon minus delta time length, okay. And then we can think that okay, the Brownian motion is as if starting from W delta itself, okay, another Brownian motion you can imagine W delta itself, and then this is basically saying that okay, it does not exit the domain before this time interval, that epsilon minus delta, it does not exit. So tau d is more than epsilon minus delta given W delta is starting point. So this inside conditional probability is exactly same as this this conditional probability. Now I have written G delta in terms of tau delta, correct? So now we write down this expectation. When we do this expectation, we do in the following manner, that W delta is having some particular value, okay, say y. So here we write down 0. Why do we do that? Because it is a starting point, correct? Since it is starting point, so now I mean it is like abuse of notation. You can, because this tau d is actually exit time of the Brownian motion, say W prime, which starts at W delta, correct? And then we are not using W prime notation, we are abusing of notation, we are writing that as W itself. Okay, so we write down W0 is equal to this point W delta. Okay, so and then this is the whole thing is function of W delta. So this is just a function of W delta. So the expectation would be that function evaluated at y and then integrate with us to the law of W delta. Okay, so that is how we find out the expectation. So this probability tau d greater than epsilon minus delta given W0 is equal to y, integrate with respect to the law of W delta. So here this is conditional law, because W0 is equal to x should always remain there. Okay, fine. Now what we observe is that in this integration, the integrand is just a probability. So it is between 0 to 1, it is bounded, correct? It is a bounded measurable, correct? This is measurable function of y. And then this integrand, okay, so this integrator is a measure, okay, but this measure is not a single measure, it is a family of measures, because it depends on delta, it depends on x also. Okay, so this family of measure has one nice property which we would require for the convergence, that this is tight. Okay, so this is a tight family of probability measures. What does it mean? That for Brownian motion here, if you take a compact set and then beyond this, I mean given epsilon, you can always find out compact set such that beyond this the probability measure of that would be less than epsilon for all the members in the family. Okay, so that is the thing, and that is true here because here delta is between 0 to epsilon. Okay, you are not changing delta much. You are not changing delta. What does it mean? That you are not changing variance much. So that means the family of normal random variables, that family has bounded variance. Okay, and x is also like we are going to take x tends to 0, so it is in the neighborhood of 0. Okay, so that means the mean is also bounded. So we are using, I mean this is tight family is coming due to the nature of the family of normal random variable. If you have family of normal random variables, okay, the distributions, and that is coming from with bounded mean and bounded variance, then corresponding family of the distributions is tight. So we are using that property. So this is tight. Okay, so now we can use Vitalis theorem. Okay, we can use Vitalis theorem because this is tight and this is boundary measurable. Okay, to take delta tends to 0. Okay, so if delta tends to 0, so then that limit can go inside. Okay, using Vitalis theorem. Thus, Vitalis theorem is applicable to show continuity of G delta, because if we put delta tends to 0, what we are going to get? I mean, this would become p tau delta greater than epsilon, this thing. Okay, so here I am writing here the d delta, okay, is going to this ws belongs to d for all s between 0 to, I mean open 0 to epsilon closed, correct, because here delta this becomes 0, and so the tau delta is more than epsilon. So basically saying that the Brownian would stay inside the domain at epsilon and less than epsilon. Okay, and here this w delta we have is, so this delta is going to 0, so we cannot assure that equal to 0, but more than 0 we can assure on the right hand side of 0. So the ws is in d for 0 to open 0 to closed epsilon, because that anyway we have actually started from delta to epsilon, correct. I mean that is the main thing, correct. So as delta tends to 0, we are going to get, I mean actually this you can see from directly from here. Okay, so here, so as delta goes to 0, you get open 0 epsilon closed here. So this part would leave us here, the G delta x converges to this. And what is this? This is basically leaving 0 aside and then talking about this. So this is not tau delta, but this is sigma delta. This basically sigma delta is positive. So this conditional probability is conditional probability that sigma delta is more than epsilon. Okay, given w0 is equal to x. Okay, but this probability is nothing but gx. So gx is defined this way. So g delta decreases. Why does it decrease? It decreases because whenever I am decreasing delta, that means this interval is becoming larger and larger. And here this event is putting condition on Brownian motion path on the interval this. Okay, and then if you increase the length of the interval, that means you are putting more and more conditions. Okay, so the event is becoming smaller and smaller, so probability is becoming smaller and smaller. Okay, and g delta decreases as delta goes to 0. So this decreases and g delta is so from here, as I told that, okay, since Vitalis theorem can apply to show that, okay, this is continuous function, and then we know that this is converging to gx. Okay, I think I did not say it quite completely, that I mean when we use Vitalis theorem, we change x also. I mean to show that it is continuous in x, then that limit goes inside, because I did not talk much about x, but that is important because that would give me that d delta is also continuous. Okay, since g is the limit of a decreasing sequence of continuous functions, therefore g is upper semi continuous. Okay, so now when we have obtained that this function is upper semi continuous, we can use the property of upper semi continuous function. So that we are doing it here. that namely that when you take lim sup x tends to 0 g x, that would be less than or equals to g 0. Okay. So, that is the property of upper semi-continuous function we are going to use here. So, let us see how do you use here. So, as 0 is regular, the regular point. So, we know that from the definition of regular point, the sigma d is equal to 0, that probability would be 1. Okay. That is a regular point, and that implies that g of 0, which is sigma d greater than 0 given this thing, okay, where epsilon is fixed. I mean, I am not writing g epsilon, I mean, because although it depends on epsilon, I am fixing epsilon something. Okay. So, I am not repeatedly using it, but of course, g depends on epsilon, but epsilon we are not changing. So, now this thing would be 0 because sigma d is equal to 0 with probability 1. So, it is strictly more than epsilon, that would be having probability 0. So, that is true for all epsilon positive. So, does not matter whatever epsilon we choose, okay, g of 0 is 0. Okay. So, any positive epsilon we choose, g of 0 is 0. Now, for every positive epsilon, again we are fixing epsilon, okay, and then lim sup of conditional probability that the heating time is more than epsilon, okay, that we are counting here, and then that is less than, or I mean, basically that W0 is equal to x, okay, and we are saying that, okay, tau d is more than epsilon, and if I replace tau d by sigma d, I know the sigma d is always greater or equals to tau d. So, that would be more than I mean, this implies this. Okay. So, since this implies this, so this is a superset. So, I would get that less than or equals to sign here. Okay. So, here x belongs to d is all over the places, but I am not writing here. Okay. So, we get this probability, but this is exactly g x, this is the definition of g x. So, lim sup g x, and then we are using the upper semi continuity property of g to get this is less than or equals to g 0, but g 0 is argued here that it is 0 for any epsilon whatever you choose. So, we got that this lim sup tau d epsilon greater than epsilon, this probability goes to 0. That was precisely the statement in 3. Okay. So, that is proved here. Okay. So, I mean, this proof part is a little roundabout way, because actually just to passing to the limit and arguing that this goes to 0, we had to cook up this function, and then using this property of the function, and to achieve that we had to consider g delta. Okay. Otherwise, basically this is the main part. Okay. So, 1 implies 2, 2 implies 3 is done. So, the whole proof would be complete if we can establish that 3 implies 1. So, or in other words, that, okay, this limit this tau delta greater than epsilon goes to 0. Actually, in that I do not have lim sup, okay, but here we are using, but because if lim sup is 0, then everything would be even if limit exists, that would also be 0. Okay. So, assuming this, we have to prove that the continuity of the conditional expectation of f of this thing, where f is any bounded measurable functions continuous at 0. Okay. So, that is for any such functions. So, there is a large class of objects. So, here we actually require that conditional probability is this inequality, which we have already shown in the last lecture. So, since I need it here in this page, so I just pasted it here to show 3 implies 1. Okay. So, it has only 2 slides. Okay. 3 implies 1. What we do, we consider this conditional probability, that conditional probability that W tau d minus W 0 is less than r given W 0 is equal to x. Okay. So, here what are you doing? We are doing that, okay, wherever W 0 is inside the domain, if x is inside the domain. Okay. I am not writing every time, but x is always inside the domain. Okay. So, because if x is outside the domain, then this will be exactly 0, correct? I mean, yes, W 0, I mean, this would be exactly tau d would be immediately same as this. Okay. So, is inside the domain, and then consider the exit time of W tau d wherever it hits the boundary, and you take the norm, the difference, okay, and that is less than r. Okay. Of course, I mean this is just a straightforward, because this is a probability after all, so it is less than or equals to 1, but this probability would be significant or I mean okay, non trivial only if you are very close to the boundary, correct, because otherwise it would not be in the ball of radius r inside there. Okay. So what we do is that we now consider intersection of another event. So tau d minus w0 is less than r. So basically that is saying that okay, that wherever it hits the boundary, the distance of that point from the initial point is less than r. So instead of that, what we are doing here, another smaller event, there we have there that wt and w naught. Okay. So the maximum distance, okay, that is less than r during epsilon interval. So here it is a random time, but we have taken a fixed time epsilon. Okay. During this small interval 0 to epsilon, wt never exits the r radius ball of w0. Okay. So that is this event. Okay. So of course this is a smaller event. Okay. And we also say that tau d is less than or equals to epsilon. So tau d is less, I mean otherwise this is not smaller, it's the intersection of these two. The tau d is less than or equals to epsilon, and during 0 to epsilon wt never exits r ball. Okay. So this implies this, of course. Okay. So this is a smaller event, so we get greater or equals to sign here, given w0 is equal to x. Now a intersection b, so p of a intersection b is greater or equals to p of a minus p of b complement. So we are using that. So p of this event we are writing here. Okay. So here while writing, w0 we are taking as 0 here, because it does not matter, because for this event is concerned. Okay. So I mean wt minus w0 less than r given w0 is equal to x. If I replace x by 0, and then this w0 will also be 0, and then this norm of wt less than r, we would ask. It has the same probability. Why? Because like x would be the starting point, and it is like you are starting a new and you are calling that as origin, and then I mean you cannot do this kind of I mean changing when say tau d is concerned. Why? Because when you change, actually you become possibly closer to the boundary or farther to the boundary, all the probability would change. But here we do not have tau d. I mean we have separated tau d basically. So this is a fixed time interval. So this is fixed time interval. So it is just saying that okay, if one starts from point x, the Brownian motion starts from point x, and wt minus w0 is and wt is within the r radius ball. Okay. What is the probability of that? It is the same that of instead of x you start from 0 and you consider ball of radius are around 0 instead of around x. Okay. So this event, the probability of this event, conditional probability would be same as the conditional probability of this event. Okay, where w0 is equal to 0. Okay. And then b complement. So this is b complement, this complement tau d is strictly greater than epsilon, that is the complement. Now we see that we have fixed epsilon, okay, and we take x tends to 0. Okay. So here when you take x tends to 0, then we actually are talking about the third condition, correct, that when epsilon is fixed, probability of tau d greater than epsilon given w0 is equal to x, and limit x tends to 0, that is 0, correct, that is the third condition. Okay. Is third statement. Okay. Third statement. So we are using this third statement. So here I mean this is the place where I am using third. 3 implies 1, correct, we have to use 3 somewhere, some point. So here we are using that this part goes to 0 as we take x tends to 0. Okay. But this does not depend on x. Okay. So this remains unchanged, and then we take epsilon tends to 0. So first x tends to 0, this part would become 0, and then this part would remain, and then we are going to take epsilon tends to 0. Now this of course depends on epsilon. Okay. but this 0 does not depend on epsilon. Okay, but this I mean how does it behave if epsilon goes to 0? This is saying that you are starting your Brownian motion from the origin and asking that between 0 to epsilon time, okay, the maximum distance what the Brownian motion has traveled, and that is less than r. That probability, I mean Wt we know is a normal random variable, okay, but it is maximum for all possible these things, okay. So, we know that how Brownian motion behaves between 0 to epsilon. If you take the maximum of that, okay, so that probability one can actually find out using that reflection principle, okay. So, that probability would converge to 0, correct, because this would be, I mean beyond the ball of radius r, that probability would go to 0. On the other hand, this would remain in the ball of radius r, that probability would become 1, okay. R I am not changing, r is fixed, so that would converge to 1, okay. So, this is true for all positive r, okay. So, by first letting x tends to 0 and then epsilon tends to 0, we are going to get that this. So, here in this probability, okay, where r is fixed and x tends to 0. So, this is between 1 and 1, okay. So, this limit, okay. So, basically this is 1. So, this limit goes to 1. So, limit w tau d minus instead of writing w0 I am writing x here, because it is given that w0 is equal to x. So, probability that w tau d minus x is less than r given w0 is equal to x is equal to 1. Okay. So, it is not yet the proof is not yet done. So, we have just obtained this from this tau d, okay, just from this this property that this goes to 0, we have obtained this this result, okay. Now, from here we need to actually get the statement of 1, the first statement. The first statement is that for all bounded measurable function f which is continuous at 0, for that it is true that expectation, constant expectation is continuous. Okay. So, how to go for that? So, here from probability to go to the expectation of a function. So, we understand that we need to use some measure theoretic approach here, okay, some extension kind of things. So, what we do is that we take some ball of radius r, okay. So, if x is in the ball of radius r around 0, so I mean whenever I do not write around 0, because this is default for my notations, that ball is like if I do not write down the center, that means 0. Then, so first we understand what is this. Br of x is the ball of radius r around x, and B2r is ball of radius 2r around 0. Since x is in Br, so x is less than r distance away from origin, and around x I have another ball of radius r. So, this ball would be inside the ball of radius 2r around 0, correct. So, this function is larger than this function. So, it does not matter what where I evaluate on. So, we evaluated w tau d, okay. So, this is immaterial, but this function is more than this function, okay. So, we have this inequality. Hence, for any r positive, so what we do is that we are using we are writing what is written here, the last line actually, and same thing I am writing, x tends to 0, probability that norm of w tau d minus x norm of that is less than r given w0 is equal to x is equal to 1. So, this would imply that, so here r is there. So, what we do is that this, I mean this part is same as this part, correct, because w tau d minus x is less than r, or in other words you are saying that w tau d is in the ball of radius r around x, or in other words you are saying that this value is equal to 1, okay. So, this value is equal to 1. If this value is equal to 1, of course, this value would also be a 1, because this is cannot be smaller than this value. So, this event implies that 1 B2r of w tau d is equal to 1, okay. So, this is actually a larger event. So, if this converges to 1, so this would also converge to 1, okay. So, limit x tends to 0, 1 B2r w tau d is equal to 1 given w0 is equal to x is equal to 1. So, this is the way actually to go to the general function. First we talk about the simple function, correct. So, here we are doing that. Okay. So, now what we do is that probability of a set is same as expectation of indicator function. So, expectation of, for the time being you forget about f0, expectation of indicator function of this, correct, indicator function 1 of b2r of w tau d, okay, because this is the event. I mean this is equal to 1, that means that w tau d happens. So, probability of w tau d happens is same as I mean happens means it is inside the b2r. Okay, so that is like a conditional expectation of 1 b2r w tau d given w0 is equal to x, but this is 1, but then you multiply f of 0 both sides. So, you get f of 0 is equal to this. Okay, so now we are going to use the continuity property of f at 0, okay, and also boundedness of f on the boundary, okay, boundary measurability, because when f is a boundary measurable function here, so we can approximate the integration by some another function, okay, which is exactly same as f, except a small ball around 0, and there it is taking value of f of 0, and since f is continuous at 0, so given epsilon there is a neighborhood on 0 such that f of x minus f of 0 would be as small as epsilon, okay, for every point in the neighborhood, and that neighborhood, the 2r would serve the neighborhood for me. Okay, so I can, and the probability measure is finite there, correct. So, I can actually for integration of the whole function, I can actually write down, say, expectation of f w tau d. I can write down it in two parts. One is an approximation around in that neighborhood of 0. There I am replacing f of actual function by f of 0, and by doing so I have one error bound, okay, and outside I am keeping the same function. And if I do that, okay, so let us see this thing, that from here, that this is 1, this limit. So, that means that in the complement this would be 0 with probability 1. So, in the complement this is 1 is that probability would be 0, the complement. So, if I even multiply a bounded function here, f of this the w tau d with this indicator function, okay, I would still again get the expectation to be 0, because here the domain here, I mean this product, it is multiplied with something, okay, and this is bounded and this is multiplied, and here this probability is going to 0. Okay, so this random variable is 1, that probability goes to 0, that means 0, it is 0 almost surely, it is convergent to 0 almost surely. So, this would go to 0. So, this is the remaining part basically on the complement of the ball, okay, of the 2r. So, there this expectation, this part would go to 0, and inside this is the scenario, and f is continuous at 0. So, with all these things together we get this result, that limit extends to 0, expectation of f of w tau d given w0 is equal to x is equal to f of 0. Okay. So, this is the continuity property, this is the first statement. Okay, thank you.